3.1, identify pairs of lines and angles. In Unit 3, parallel and perpendicular lines. As we talked about in the previous unit, there are two main angle pairs that we want to keep coming back to over and over and over again in this course. The first one is called a linear pair. A linear pair is when two angles are adjacent. Remember, adjacent means just right next to each other. So if we're looking at this first picture here, we can see that angles 1 and 2 are a linear pair because their non-common sides are opposite rays. So if we're looking at these two angles, this would be their common side, and their non-common side would be this guy, who is an opposite ray to this guy. And it's important to remember that in a linear pair, together, they are supplementary. And remember, supplementary simply means that that's when two angles will add to be 180 degrees. Our second type of angle is when, angle relationship is when two angles are vertical angles. Vertical angles simply means they're going to share a common vertex and be opposite from each other. Okay, so for example, angle 3 shares a vertex with angle 6, and they are on opposite sides of that vertex. So angle 3 and angle 6 are vertical angles. Likewise, angle 4 and angle 5 share that vertex and are on opposite sides of it. And it's important to remember that when two angles are vertical angles, that means they have the exact same measure. And in geometry, we would even say that they are congruent to each other. So let's look at this example. It asks us to find the value of x and y. So how do we begin a problem like this? Well, the first thing I would do is I would just start looking for relationships. The first relationship I see is between the angle 9x plus 20 and 7x. Together, those two angles form a line. And because they form a line, we call them a linear pair. Therefore, when we add them, they have to be equal to 180 degrees. The other relationship I see is between 2y and 7x. 2y and 7x are vertical angles. And because they're vertical angles, share the same vertex and are on opposite sides of that vertex, that means they have to have the same measure. Okay, now that I have found relationships between the angles, now I want to use those relationships to create an equation to solve. Let's begin with 9x plus 20 and 7x. We have said that because they are a linear pair, they have to add up to be 180 degrees. So I would simply write 9x plus 20 plus 7x has to equal 180. From here, all I need to do is solve it. Then I'll look at my other relationship, 2y and 7x. And we've said they have to have the same measure, meaning we could just set them equal to each other. This one's a little more challenging to solve because it has two variables in it. So what I'm going to do is I'm going to solve my equation with one variable and use that solution to find this guy. I'll show you what I mean. Beginning with this yellow one, I'm going to combine like terms. So I'll add 9x and 7x, and that will give me 16x. And then I'll subtract 20 from each side of the equation to isolate x, leaving me with 16x is equal to 160. Then dividing by 16, x is going to equal 10. And I have my value of x. that value of x is going to help me solve my orange equation 2y is equal to 7x. Because now I can solve for y by substituting 10 in for x, leaving me with 2y is equal to 70. Dividing by 2 leaves me with y is equal to 35. And now I found the measure of both x and y. If I wanted to check my work at this point, I absolutely could. I know that these have to be the same measure, so this would be a really easy way to check. If I replace 35 here, right, I would say 2 times 35 is equal to 70 degrees. So I know that that measure of that angle is 70 degrees. If I wanted to check this one to determine that it's also 70 degrees, I would find x, which is 10, and I would plug in 10. I would get 7 times 10, and 7 times 10 is also 70, telling me that these are truly vertical angles and I've done my algebra correctly. Okay, let's move on. Let's look at the relationship between some lines. Two lines that do not intersect are either parallel or skew. Maybe you've never heard skew lines before. That's okay. We're going to talk about it today. Two lines are parallel if they do not intersect and are coplanar. Remembering from our previous unit, coplanar means are on the same plane. So we're looking for lines that are on the same plane but do not intersect. Two lines are skew lines if they do not intersect, just like the parallel lines, but are also not coplanar. So in this picture, M and N are coplanar. But if I had a line down here on plane U, let's call it line L. L would be skew with these lines because they do not lie on the same plane. And remember that when we have two planes that do not intersect, we call these parallel planes. So let's look at this picture. And let me erase my drawing here. Lines M and N are, so we're looking for the relationship of lines M and N. I see that they are on the same plane. And I see that they have these red triangles, which is a way to note on a diagram that two lines are indeed parallel. And you'll often see this notation, M, and then two vertical bars, and then N. And this means M is parallel to N. Lines M and K. These are called skew lines. M and K do not intersect each other, and they are not completely on the same plane. Planes T and U are parallel planes because they do not intersect. Line K and line N are intersecting lines. And there is a plane that would contain them. So try to imagine here that there's this plane, that would come through right here that would connect these two lines. Let's take that thought about parallel lines skew lines. And let's look at this box. So think of think of each segment in the figure as part of an entire line. Which line or lines, plane or planes, in the figure appear to fit these descriptions? Description A, line or lines parallel to CD that contain the point A. Let me get a something to draw. So I want it to be parallel to CD, but I want to contain the point A. So here are the lines that I see that contain A. Here's one, but it can't be parallel because it connects at D. I see this line, but AH and CD are not on the same plane. I see this line, but we have the same issue. And last, I see this line. Okay, so they are not intersecting with each other. And they are on the same plane. So we're looking at AB here. And the plane that they share would be the top of this box. There are other lines that are parallel to CD. HG is one of them, and EF is one of them. But the only one that goes through A would be this AB one right here. Now we're looking for lines that are skewed to CD and contain the point A. So again, here's E. And we're still comparing this to CD, but now we want to be skew. Remember, skew means does not intersect and is not on the same plane. So we already talked about all these lines that go through A. So AG is not on the same plane and would never intersect. And AH is not on the same plane and would never intersect. So these would be my two lines that are skew to CD. C, lines perpendicular to CD. Perpendicular. Remember, perpendicular means meets at a 90-degree angle. We also call a 90-degree angle a right angle, in case you have forgotten this vocabulary. So you see the red boxes in your diagram to the right, telling you that these meet at right angles. So therefore, all corners of this box will be meeting at right angles. So we want to be perpendicular or meeting at a right angle with CD. So we're still talking CD here. And contain the point A. So if we're going to be perpendicular, we have to be on the same plane. So CD and A share the top of this box. That's the plane they share. So on the top of this box, I have AD and I have AB. And I'm trying to figure out which one of these, AD or AB, would be perpendicular. AD. It shows this right here. Again, there are many sides that are perpendicular, or excuse me, there are many lines that are perpendicular, but only one that goes through A. D. planes parallel to EFG and containing A. So we want to be parallel to EFG. EFG. EFG would be the bottom of this box. Parallel to the bottom of this box would only be the top of this box. Every other plane is going to intersect it somewhere. And it does indeed include the point A. Parallel and perpendicular lines. Two lines in the same plane are either parallel or intersect in a point. Through a point not on a line, there are infinitely many lines. So if I were to draw a point, that's what this first thing is saying here. If I were to just draw a point, I could draw an infinite number of lines through that point. If there are no restrictions, I could just keep drawing lines an infinite, ooh, that's not a line, that's a curve, number of times through this point, okay? So that's this first thing. That's what it tells me. Through a point, not on a line, there are an infinite number of lines that go through that point. Exactly one of these lines is parallel to the given line, okay? So let's say we have a given line. Let's call it L. And we have a point not on L. Let's call it P. If I want to draw a line parallel to line L through P, there is only one way I could draw that where they would be parallel to each other. That's what that next part says. And exactly one perpendicular. So that means given line L through point P, there's only one way that I can draw a line perpendicular through L. So that's what this paragraph is explaining to us, that if we're given a point not on L, there's only one line parallel through P and only one line perpendicular through P. Even more specifically, we have a parallel postulate, number 13. It says if there is a line and a point not on the line, there is exactly one line through the point parallel to the given line. And if there is a line and a point not on the line, there is exactly one line through the point perpendicular to that given line. Now would be a good time to pause and take notes. The given line markings show how the roads are related to each other. So as you can see in the diagram, they have CE, a street, BF, a street, DA, a street, nope, not DA, I'm sorry, CA, a street, DM, a street, and EF, a street. It says name a pair of parallel lines. When you're naming a pair of parallel lines, look for the markings on the line. So I see markings here and here. And these arrows are the arrows that tell us that DM is parallel to EF. And they, of course, wrote MD and FE instead of EF and DM, and that's fine. B says name perpendicular lines. Again, we're looking for markings, and this one's actually a little bit difficult to see. But if you look right here, you can see this 90-degree marking or this right angle marking. That's what's going to tell us perpendicular lines. So that 90 degrees is falling on DM and on this line. And there's lots of ways that I could name this line. I could name it BM, MB, BF, FB, MF, FM. Lots of ways that I could mark this. Any way you want to write it, though, these are our two lines that are perpendicular with each other, MD and BF. Oops, I didn't mean to click that already. Oh well. Part C says, is FE parallel to AC? So as I'm looking at this, and I'm gonna just grab a color here, maybe one that I have not used. How's green? There we go. So FE is this line. Whoa, I missed, but you get the idea. And AC is this line. And the question is are they parallel to each other? Well, I think you can just look at it and see that at some point, these two lines are going to run into each other. So no, they're definitely not parallel. Now, the reasoning is actually that we've already said that through point M, DF is parallel to that line. And remember, there can only be one. And if there can only be one, then no, they cannot be parallel. The end. Now go practice the quizzes before you take the quiz for 3.1.